Hello everyone. My name is Frederik Durhuus. I am a PhD student at the Technical University of Denmark with Katrine Fransen and Marco Belegia as supervisors. I am here to present some work we did on the aggregation of magnetic nanoparticles in liquid, specifically the effect of superparamagnetism on aggregation. And this plot, which will also be the conclusion, I will get back to this, essentially summarizes our work. We introduced the notion of debonding time for these two particle aggregates and used it to show that, surprisingly enough, there is no connection between superparamagnetism and aggregation. But to build up to this, let's start by introducing the concept of superparamagnetism. So we imagine our particle as a sphere with an arrow for the direction of the magnetization. And then we have uniaxial anisotropy, perpendicular to these blue-green circles. Can you see the mouse in my presentation? Anyway, there is therefore two equivalent energy minima with the magnetic moment perpendicular to these blue-green circles. And when we run computer simulations of this, as shown here are some simulations with room temperature thermal fluctuations, we get different behaviors depending on this anisotropy energy. It can largely be explained by this key parameter sigma, which is the ratio of the anisotropy energy barrier to thermal energy. When we have a moderate value of sigma, we have very large thermal fluctuations and a tendency to oscillate between the two energy minima, while at much higher sigma, the magnetic moment tends to stay in one energy valley, in which case we say the particle is blocked, at least on the time scale of this simulation. Now, the literature consensus is that because of these thermal reversals, the magnetization averages to zero over time. It keeps changing direction, so if you integrate in time, you get zero magnetization. And this should mean that the magnetic interaction between superparamagnetic particles is negligible, or at least greatly reduced. And this is often used to explain the experimental observation that superparamagnetic particles are easier to keep apart. It's easier to stabilize a colloidal suspension of superparamagnets than blocked particles. Now, we find that the first and third point are correct. But this argument that magnetic interactions are negligible does not hold. There's a misunderstanding in at least part of literature here that I will try to clear up. So as a model system, we exclusively consider pairs of uniformly magnetized nanoparticles. We include the magnetic dipole interaction, we include uniaxial anisotropy, and we have steric repulsion, which is this short-range surface potential, which essentially makes the particle solid. It prevents particle overlap. So these are all the degrees of freedom, the magnetic moment directions, the anisotropy axes, and the relative position. In addition, we imagine the particles in some liquid, here illustrated with water molecules, which gives some viscous drag, and it also leads to thermal fluctuations in the mechanical degrees of freedom as the fluid particles collide with the magnetic particles. And all of this we simulate with Longeron dynamics using a Python code I developed. So that is the model. Now, to quantify aggregation, we introduced this notion of debonding time. So we initiate the particles in the dimer aggregate. So in surface contact, magnetic moments and anisotropy axes all aligned. And then we look at how this evolves in time with all degrees of freedom. And we track the distance as a function of time. And we say that when it reaches a certain critical distance, here 3 times the radius, the bond is broken. And so we track these points in time, in particular these red dots for different simulations that differ only in the thermal fluctuations. Okay, so doing this for many particles, in fact, 250 pairs for each parameter set, we can track the number of unbroken bonds at a given point in time. And this turns out to decay exponentially. Here we see some exponential fits for different temperature values, and we have a very clear exponential dependence. And this gives us our debonding time. It's not the most direct measure of aggregation, but it gives us something quantitative that we can use to very clearly get the parameter dependence of the stability of the aggregate and the general tendency to aggregate. And this is our results. So every one of these data points is from an exponential fit, as shown in the previous slide. We have two key parameters, sigma from before, and lambda, which is the ratio of the characteristic dipole potential to thermal energy. And what we see is a very strong dependence on lambda. This is a logarithmic scale, so we have an exponential dependence on lambda, which is what typically happens when you have thermal fluctuations pushing a system across some energy barrier. But we have no discernible dependence on sigma. And since varying sigma changes whether or not the particles are superparamagnetic on a given time scale, this shows that we have no connection between superparamagnetism and aggregation. And this is a somewhat surprising conclusion. So you might think that there's something subtle going on here. For example, it might be a timescale issue. Maybe the addition of dipole interactions changes the time scale of these superparamagnetic reversals so that all the particles are blocked. Well, this issue we checked explicitly by also simulating the magnetic dynamics of fixed D-mer clusters. So we removed the mechanical dynamics and just look at the magnetic moments fluctuating. And we get these very clear thermal reversals. In fact, the moments are very strongly correlated because of the dipole interaction. So they tend to flip as one. And we then look at, again, 250 pairs of particles for every parameter set. Averaging over those, we get the ensemble averaged magnetization as a function of time. And this decays exponentially. I mean, this is the phenomenon of superparamagnetic relaxation. This average decays in time. And again, we get good exponential fits for different parameter values. So we can get the Niel relaxation time as a function of the relevant parameters. Here we compare the two timescales. Note that it is essentially the same axes. And we see that we have relaxation times that are both significantly shorter and significantly longer than the debonding time, which shows that this is not a matter of relative timescales. Irrespective of the parameter range, anisotropy and superparamagnetism does not affect aggregation within this model and more generally. But at first glance, this contradicts the experimental observation that superparamagnets are easier to keep apart, easier to colloidally stabilize. And the reason for this is a coincidence. The parameter which actually matters is lambda, but lambda and sigma have the same scaling with respect to size and temperature, radius to the third power per temperature. And when you look at the ratio of these two parameters, all you're left with is a constant of nature and two material parameters, magnetization and anisotropy. And this ratio tends to be around order unity, within plus or minus 1 order of magnitude. So there is a very strong correlation between the parameter that governs superparamagnetism and the parameter that actually matters for aggregation, which is why superparamagnetic particles are observed to be aggregate less, to be more easy to stabilize. It is a coincidence of parameters. But very importantly, the anisotropy constant itself does not impact aggregation. So there is a significant difference and also a conceptual difference. And we can understand this in a bit more detail if we look at some statistical physics. So first of all, the reason that we have a force of attraction at all is because the magnetic moments are correlated, as we saw before. There is a statistical tendency towards alignment. So even as they fluctuate back and forth, there is an average force of attraction. Here we simulated this force of attraction at different distances with positions fixed, but all the different rotational degrees of freedom. And we also have some analytical results for small lambda. The dash curve is if the particles are perfectly aligned. So what we see is that the thermal fluctuations, they do reduce the force, the average force, and it gives a different dependence on distance. It's shorter range and therefore more localized, but it's still there. And it is independent of sigma in both the numerical and analytical calculations. And I do not have time to go through the whole statistical physics derivation, but the best way we found to intuit this result is that mechanical rotation allows you to reorder the magnetic moments without crossing any energy barriers. You essentially circumvent the anisotropy barrier by rotating the whole particle rather than just the magnetization. And this is why sigma does not matter for equilibrium effects like aggregation or static susceptibility. Now, there is a difference between the time scale of magnetic and mechanical rotation. Magnetic is orders of magnitude faster. So for some rapid time-sensitive phenomena like high-frequency hysteresis and dynamic susceptibility, sigma does matter, but not for aggregation. And this is a main conclusion of our study. So to summarize, here is the plot from the introduction. We introduce the notion of dimer debonding time. We have an initial condition like this. We have a critical bonding distance. This allows us to compute this quantity that says something about the stability of aggregates and the tendency to aggregate. And varying the dipole coupling strength and anisotropy, we find no connection between superparamagnetism and aggregation. And that is the full talk.
Thank you, Dr. Frederik, for this amazing presentation. So if you have any questions, don't hesitate to ask. We have 2 minutes for questions. So I have a question myself. So what is the origin, like microscopically, of superparamagnetism? So I got that the main result is probably not the correlation between superparamagnetism and aggregation, right?
Yes.
So, so what's the microscopic origin of superparamagnetism in the model?
Yes. So if you have a magnetic moment in a magnetic field, we all know it precesses.
Yeah.
But in order to align with the applied field, there has to be some damping mechanism. And whenever you have a damping mechanism, you have thermal fluctuations. That's called the fluctuation dissipation theorem.
Yeah.
So there are thermal fluctuations in the direction of the magnetic moment. And so these thermal fluctuations can cause it to cross the energy barrier. And that's essentially it. It's a consequence of thermal fluctuations in a system with an energy barrier.
Yeah. Okay. Makes sense. Yeah. Thank you. You can also post questions on the chat. All right, let's thank again Frederik for the nice presentation.